All right, working with triangle similarity, the angle-angle theorem, we want to know how can similarity transformations and the angle-angle similarity theorem be used to prove triangles are similar. So we want to be able to identify the composition of similar transformations and mapping of two triangles and complete the steps to prove triangles are similar using angle-angle similarity theorem. So when we're talking about similarity, we are going to need to remember some of those words. We have corresponding angles, and that's a pair of angles that have the same relative position in two congruent similar figures. Corresponding sides, well, a pair of sides that have the same relative position in two congruent or similar figures. And let's see what else. Dilation, of course, we want to remember that a dilation preserves the corresponding angle measure and creates equal ratios between the corresponding side lengths based on the scale factor of the dilation. And let's see here, similarity transformations is a transformation on the plane that preserves our angle measure. So if I wanted to draw a couple of pictures here, I have this triangle, and this is ABC. And then I may have a dilation inside of it, and that would be A prime, B prime, and C prime, and that would appear to be a reduction. And as we said, corresponding angles, angle A corresponds to angle A prime. That would be corresponding, just like angle B corresponds with angle B prime. And then a corresponding side, well, side AB corresponds to side A prime, B prime. So that's where visually what they're talking about when they talk about corresponding angles and sides. And then, of course, this is possibly a proportional length here between AB and A prime, B prime. But we'll get more into that here momentarily, but just so you know, just a visual on what they're talking about. So as I mentioned, if we look at this, we have a image drawn of a dilation, and the center of dilation is going to be O. So I have a dilation. The center is going to be O, and if I look at the scale factor, well, I know that I have the scale factor. I have A prime, B prime is the same as AB, and I know that I have A prime, C prime, and that is going to be the same as AC, and then I also have B prime, C prime, which is going to be the same as BC, which is going to be equal to, well, if I had said it was 2, it's going to be 2, scale factor of 2. And if I look, I can say that for my orientation, I have OB and then OB prime, and OB prime is going to be the length of 4, OB is going to be the length of 2, which is going to be 2, which would give me my scale factor, because that is something that I can actually identify given the values there, because we have 2 and 2, which gives me 4, and then of course OB or BO, is going to be 2. So I'm able to figure out that scale factor from that, or the scale factor, the dilation from that. So as we move on here. Okay, and then watching for transformations or the sequence of transformations. And we could want to know here, say, can we map triangle ABC to triangle DEF using a sequence of transformations? And I do believe that the answer would be yes. We may have to look at its orientation, and if you notice just that my 100-degree angle is up here, my 100-degree angle is up here, I have my 41-degree angle sort of facing each other. So I could assume at some point in time that this must have been some form of reflection over some point, because the orientation is not the same. But I can end up mapping it that direction. Just for example, if I had, nope, don't want to do that. if the triangle had been, one triangle had been ABC, right? So clearly it is going to be the same degrees, but then I turn around and I have one of the triangles is much larger than the other triangle. And I could say, well, it appears to be just a transformation, or is it just a dilation? And I would say that it is not just a dilation, because we would have had to, not only has it dilated because it has enlarged, right? We've enlarged, but it has also been flipped, right? It has been reflected. So it is not just a dilation. We have to look at it and say, hey, we were reflected and dilated. So looking for multiple transformations is going to be the key here when we are talking about similarity, because it may not be as simple as just there. So if Okay, so what we're looking for here is we are looking for similar transformations. So we can see that we have started off with triangle LNM, and we have what would appear to be a dilation where we have enlarged, and it looks like it also is a second transformation because of its L double prime or N double prime. And so we're trying to figure out similar transformations is one that preserves the angle measure. So the two figures are similar if and only if the similarity transformations mapping, if there is a similarity transformation mapping from one figure to the other. And right now we don't have that, but could we somehow be able to do that? And there is a in-between mapping that we are missing out on. So if I were to look at it and I could say, hey, it appears that the length of NM is going to be 1, 2, 3, 4. The length of NM is 4. The length of NM double prime is going to be 1, 2, 3, 4, 5, 6, 7, 8. So that is times 2. And then if we look at the length of LN here, 1, 2, 3, 4, 5, and here it is 1, 2. 1, 2, 3, 4. So this one is 4, this one is 2. So it looks like we probably have a scale factor in there of 2 somewhere. And if I had to guess, it's probably going to be the origin. Just because if it's 2, right now I'm 1 away. So if I were to double that, that would place me 2 away and also increase my length by 2. So if I were to do a transformation, we know that we have 2 transformations. We have something here, and then transformation that we can think of is a dilation 0, 2. So if I were to figure out from N, if I took all these points and I dilated them times 2, let's see here. So we would have N is going to be negative 1, 1, and its dilation, so that is going to be, N prime is going to be negative 1 times 2, and 1 times 2, the scale factor. So then my new points, N prime is going to be negative 2 and 2, which places me at right there. Let's see, what is M going to look like? M is currently 3, 1, and then when I do its dilation, M prime is going to be 3 times 2, which is going to be 6, and then I have 1 times 2. So we're looking at M prime is going to be 6, 2. So that places me right here. And then finally that last point, which is going to be L. L is going to be negative 1, 3, 1, 2, 3. And it's going to dilate to negative 1 times 2, which we have already said is negative 2. And then 3 times 2. which is going to give me 6. So it looks like that is going to be -2 and 6. And if I go ahead and connect my points here so I can see my triangle. Oops, there we go, much better. It looks like my first transformation, the dilation, I've got it to the size that I need. So, well, I guess it looks like I just need to translate it down. In order to get from L1 to L7, I just need to go down 1, 2, 3, 4, 5, 6, 7 points. So it looks like I'm going left and right 0, but I'm going to go down 7. So it looks like that would be my transformation mapping to get from my first triangle to my third triangle. So just being able to break it down and look at the difference and see what can I modify to see, just play with it and see what happens. So with the angle-angle similarity theorem, what we are going to find is that if two angles of one triangle are congruent to two angles of another triangle, then the two triangles are going to be similar. And why do we say just two angles? Well, if I have a triangle and I have another triangle, and it doesn't matter the size, whether it is larger or smaller, and this angle is going to be 39, and this angle is going to be 61, and we'll just go ahead and say, well, here's another angle that's going to be 39, and this one's going to be 61. Well, I know that a triangle has 180 degrees, so all three of them add up to 180 degrees. So if I look and I say, what is that missing angle? Well, 39 plus 61 is going to be 100, so I have 180 minus 100, which is going to leave 80. So x is 80 degrees. 80 degrees. Now let's look at this other triangle. Well, we have the same thing. We have 180 degrees minus 39 degrees minus 61 degrees is going to leave behind 80 degrees. So it looks like this missing angle is going to be 80 degrees. So it doesn't matter the size of the triangle. If you have two accounted for, two congruent angles, that means the third one has to be congruent because there's only one value that I can add to that that's going to equal 180 degrees. So just remembering that the sum of the angles of a triangle are 180 degrees, and we can go from there. If two of the angles are congruent, that means the third one has to be congruent. And that's how we're able to work with triangle similarity with just two angles being congruent. Okay, so looking at some angle-angle similarity and using some of our previous learned vocabulary, I want to know, is triangle ABE congruent? Probably not congruent. Let me rephrase that. Not congruent, but similar, right? So is it similar to triangle CDE? Well, that's telling me triangle ABE, right? And then is that congruent to CDE? CDE, okay? And let's see, first of all, let's see, for similarity, I'm looking for two angles that are the same. And well, I know from looking at this that if I have, it looks like I have this segment AD and segment BC, and they intersect at point E. So that tells me that point E, is that center point, and we have this these vertical angles here, and I know the vertical angles are going to be congruent. So I can go ahead and mark that. That seems pretty straightforward and easy. If you haven't noticed, it looks like segment AB and segment CD are also going to be parallel. So we have, let's see here, angle AEB is congruent to angle CED, and then we have that AB is parallel to CD. Now, if they're parallel, that gives us some more identities. We should be able to pick out that, well, angle A here should be an alternate interior angle to angle D. And then angle C should be an alternate interior angle to angle B. So it looks like we actually have three angles that are similar on these two triangles. So I definitely have some angle similarity because I have actually all three angles are similar. So looking at that, just being able to pull those together. Now you see the orientation. The orientation needs to be understood and identified. If you'll notice, see my angles run. Thinking, just look at my congruency markers, 1, 2, 3, and over here I have 1, 2, 3. So the orientation is a little bit skewed, but they are similar triangles. You know, for example, angle D corresponds to angle A. Angle B corresponds to angle C, and then of course angle E corresponds to itself. So just keeping that in mind, that the orientation has to be sort of manipulated for those visual learners. Okay, so looking at this, as the composition, looks like we have two dilations. The dilation from the origin, scale factor of 3/2, and then the dilation from the origin, the scale factor of 1/2, is applied to the triangle RST to create the image of RST double prime. So it's that second dilation, which is not shown, of course. So what is the coordinate of S double prime? Well, the current coordinate of S is going to be right here, which looks like it's going to be -2, 6. Okay, so S, my first dilation, right? Dilation from the origin, 1/2. XY, so I have S is going to be, we said -2, 6, and is going to transform, dilate to S, which is -2 times 1/2, and then that is going to be 6 times 1/2, and so it looks like my first point for S transformed will be -1 and 3. Now we want to transform that again to the second transformation. So we have around the origin, and it is going to be transforming the XY. So we have S prime is going to be -1, 3, sorry, and it is going to transform to double prime here to, see here, X is going to be -1 times that transformation, which is 3/2, and Y is going to be 3 times that 3/2. So it looks like my new points will be -3/2 and 9/2 should be the new location for my S double prime. So -3/2 and 9/2. Without actually putting it on the graph, I was able just to do it mathematically to find those points. Look at, so just remember, similarity transformations are transformations in the plane that preserve angle measure of figures. Those similar figures have congruent angles and proportional side lengths. Similarity transformations use a scale that dilates side lengths proportionally, and then this creates similar figures. And then the angle similarity theorem tells us that if two angles of one triangle are congruent to two angles of another, then the triangles are going to be similar. Remember, we only need two triangles. The third one's going to be the same because we only have 180 degrees in any triangle. So as we continue with this, we will be able to identify those compositions and use the similarity, prove triangles are similar using the angle similarity theorem.